during about half an hour. And the idea this is to extract from the different presentation we have seen this morning, if it is possible to get some constraints on the sample return. For example, what could be the sample site, for example? Can we have some constraint on it? What kind of composition could we expect? What kind of measurements do we really need to constrain the origin, and so on? And so, for example, in the presentation I've given from the giant impact scenario, we could expect, in fact, to have, for the composition of Phobos, a mixture between the impactor, and we don't know its composition, and a mix with Mars composition. And so, if we can imagine what kind of mix is it, what kind of measurement would be very interesting to validate this scenario. So what kind of geochemical analysis, for example, and so on. So who wants to start on this point or other point? Thank you.
I will. I don't know. I guess first I'd like to say that obviously spacecraft data, whether sample return or spacecraft are there, are what are on everybody's minds, but that also since the last time we took a lot of looks with telescopes, there have been, we've come a lot further with telescopes. There's a lot more capability, you know, whether radar or something like ALMA or JWST, so we might want to keep that in mind as possible when we think of possible observations we might want to do. I think one of the key questions, like we were talking about at the earlier break, is what temperature, if Phobos and Deimos were formed via a giant impact, what temperature did that material get heated up to, and on what spatial scale did that happen? You know, could we tell whether they started out as mostly impactor material or not mostly impactor material? If everything really got heated up to thousands of Kelvin, then I don't know if we would be able to tell.
My question was going to be the same, but I thought Julian should comment on this. Yes, you. So, I mean, so what temperatures do you get for the material in your disk? Because I didn't remember, and I couldn't catch you in the break because you were talking. So.
Yeah, so it's you know, it's mostly a large impact rather than giant impact. You know, if you compare it to the Earth's moon-forming impact, so the energy is much smaller than in the moon-forming impact case, but you can still heat up material, to several thousands of Kelvin, definitely.
Okay, but do you have to? I mean, could you avoid that if one tried?
Well, I think it's hard because even if you take an impactor that's point something % of Mars and you hit that at several 5-10 kilometers per second, the amount of energy realized in the impact is it's hard to avoid. At least substantial melting. I think the fraction of vapor you get from the impact is pretty small, but it's going to be hard to avoid at least significant melting of the material, I think. But on the issue of the composition, and that's, I was just talking about that with a colleague, the question that I have is, whenever we're looking at Phobos and Deimos, we're always seeing the surface. And there's no doubt that it's a surface that's probably been heavily processed through space weathering, maybe micrometeoritic bombardment, and et cetera. And I'm wondering, what would be a good way of knowing what the deep interior of these moons is, and if there's maybe a chance that it could be a little different from what we see on the heavily processed surface.
Okay. But I wanted to maybe just ask a related question. I was going to ask Andy's question, but he asked it. But I wanted to ask another question. So if you're doing this from a giant impact, so this is a question for the room, presumably the giant impactor is well over 1,000 kilometers. So think of something much larger than Ceres. Now Ceres, we think, is at least somewhat differentiated. So I'd expect the object is differentiated. If it's something that comes from the outer solar system, maybe it has a water-rich mantle or something else, maybe an ice mantle. So what does that mean when you hit and then fragments are coming off of that? Do you have a water-rich disk? Do you have an ice-rich disk? How does the influence of water and rock in this very hot environment, how does that interact to ultimately give us Phobos and Deimos? Or can you rule that all out by the fact that the spectra or the samples are very different from that? And these are questions I have for the room that I don't have answers to. So.
I just wanted to chime in real quick about the giant impact, the thermal consequence. I'd say one thing, I think a lot of the codes being used to model these things are very good at the dynamics, very good at angular momentum. They're coarse resolution, and so things tend to shock up more than they may. The difference between a 5 kilometer per second impact, which is actually marginally subsonic, versus 8 kilometer per second or 10 kilometer per second is precipitous. So I think it's possible to preserve a substantial fraction of unmelted material. I don't know. I think it's something that really needs to be studied.
Well, just to observe, we have 70 or 80 unmelted samples from the surface of Mars sitting in meteorite collections right now. It is not impossible. In fact, that's what we get. And I think Jay Malash pioneered a way of ejecting stuff at reasonable velocities without grinding it to powder and vaporizing it. So I think there's a big difference between the average heating and average energy exchange in these impacts and the individual energy exchange and heating of an individual chunk of stuff. And that's something we need to consider. The other thing is we know what happens to melted silicates pretty well, and they certainly don't drop to 4% albedo very easily. So they tend to things like serpentine. If say your impactor was made of serpentine, if you heat that up a lot, it tends to go off and be olivine again and drive off the volatiles. And I don't think that's what we're seeing on Phobos.
I have a question for the presenters. So as far as I understand that according to the models, the impact occurred about like 4 billion years ago. And so, we know that Mars lost magnetic field around 4 billion years ago. I was just wondering whether this kind of impact can change the pattern of the thermal convection to produce this effect. Does anybody looked at this question?
So I have not looked into this question, but some people have. And the question is, I mean, your question is a good one. Essentially, if you have a boreal impact on Mars, what is its influence on the magnetic field? It's possible that event essentially does something to the interior that kills the dynamo. So ultimately, the magnetic field from that point on is dead, or it fades away very quickly. And the impactors like Hellas and Utopia and the rest are not magnetized. So that's what suggests that the magnetic field did not survive very long after that impact, or it died somewhere between the Borealis impact and the Hellas impact. So I think that's all we can say. In terms of the ages, I think the ages are not well known. So years could also be 4.5 billion years, and we don't have any idea. So it's something like that.
So I had a question for everyone who was talking about motion of regolith and ejecta and reaccretion of ejecta. Phobos can acquire Martian material through ejecta from Martian impacts. So if we're sampling and we want to either take advantage of that or avoid the Martian material that's on the surface, do we know enough to figure out where that is going to collect or not collect? For example, Dan was showing us how stuff could roll downhill from the leading and trailing apex. So does that mean the leading and trailing edges get cleansed, and the material that's gardened by impacts at those points roll down to the Mars-facing part? So do we know how that material is going to move around and evolve?
We studied in great detail the proportion of ejecta that winds up in the regolith of Phobos. Mostly because of how Phobos has only been recently close to Mars. Most of that material is going to end up in the upper maybe half meter or so, in the proportion of maybe 250 ppm, that sort of thing. There's one other paper in the literature that has a similar result, just to give you an idea of what you might be finding in the regolith and where to look. Globally distributed because impacts redistribute the regolith on Phobos, so you can look anywhere for it.
So once it's deposited, it doesn't move around?
No more than the regolith gets to work.
I had a question for the couple presenters mentioned the idea that there are transient moonlets that are larger than Phobos and closer in that then were reabsorbed by Mars. It seems to me that should be easy enough to find evidence for or against. What were the estimated sizes of these moonlets, and are there any craters on Mars that seem to match these as far as age and size?
So I think the largest that form from disk are generally of the order of like 10 to the minus 6, 10 to the minus 5 Mars masses. So it's still a pretty small amount of material that would fall onto Mars. I don't know that there's any specific trace of an accumulation of material at the Martian equator. I don't know, maybe Bill Bucky has a comment on that. I mean, he probably does. He has a comment about everything.
Doesn't mean I'm right about anything, but that's another thing. Yeah, I think, I mean, people, we looked for this many years ago, and one thing is if you have something hitting the upper atmosphere, you would expect it to sort of spiral in and hit at an angle which would almost be horizontal to the surface. You'd end up with some kind of huge elongated crater, and we don't see anything like that. But the possibility is that these things come in the atmosphere so subtly that basically they're just torn to shreds, and maybe they don't make it to the surface to make anything observable. So it could be there is no evidence, which is frustrating, but that may be the way it is.
Yeah, it's likely that as the moon is spiraling inward, they get into the rush limit, so they get tidally disrupted. How efficient that process is would need to be investigated, but it's more likely that these objects get blown apart, that eventually you get smaller objects eventually falling onto Mars, and maybe they can also get additionally disrupted in the atmosphere itself. Yeah.
Well, it's an interesting story if you have Borealis formation create Phobos. Borealis is a geologic feature that survives on Mars, so whatever happens after Borealis will survive on Mars. And so if you have 10 to the minus 8, 10 to the minus 6 Mars masses spiraling in, broken up, accumulating, you'd have something like 100 meters to 100 meters average thickness over the surface of the planet. And so, there are craters on Mars that have sedimentary deposits that are higher than the rims of the craters. And in fact, the Curiosity rover is roving around on one of those sedimentary deposits that, to everyone's perplexity, the top of Gale Crater's mound is higher than the surface of Gale Crater. And one of the big geomorphic mysteries of Mars is where did these sediments come from? So, there is a puzzle to be solved there. Maybe there's the answer.
I guess I was just going to circle back a little bit to some of the other stuff we were talking about. So, I mean, it is true that we have pieces, intact Mars meteorites that presumably move just as fast as that came out of Mars as fast as a giant impact might have hit Mars. But a lot of the characteristics we're trying to explain are going to be correlated with one another. So if you want to make Phobos out of a lot of impactor material and have it be relatively, and still have it be recognizable as impactor material today, then you have to explain why spectrally it looks like the outer, like the asteroids, and then you lose one of the potential, bonus, one of the potential explanations that we heard this morning, right? If you want to have the spectral stuff work out, then it sounds like you need to really break the debris disk down into little bits and have stuff recondensed to explain the spectra, which means that you're not going to have the impactor material kept recognizable as such necessarily. So I think it's fine, however it works out, it works out, but I think we have to make sure we're not mixing the best parts of all the different explanations to come up with a scenario that doesn't actually hang together.
I think one thing that can be said from the impact simulation with whatever resolution we have at the moment, that I think, and I'm treading lightly here, I think the material that ends up to the farthest distances where we're expecting Phobos and Deimos to maybe have formed, generally comes from the back of the impactor that is being sheared away and launched into large orbits, and that back part of the impactor generally gets less processed as the rest. So it's not completely crazy to imagine that the material from which Phobos and Deimos formed may have been that less processed impactor material, and that maybe the stuff that it was in the more inner region of the disk may have been more of a mixture, more processed material.
Which is fine, but then that means that you now need to explain why spectrally they look like the asteroids again. And that's fine, but that also puts in a constraint, which is, would need to be explained, which is fine, but.
I mean, that's an interesting question because it has to be a 2,000-kilometer body that still has this asteroidal spectral signature.
I'd like to ask a challenge question. I was too slow to ask this earlier. Well, you showed us a footprint on Mars, which is a data print of cohesiveness and compaction of the lunar regolith, which some people thought maybe wouldn't happen. So what would a footprint look like on Phobos?
I think I missed your question.
What would a footprint, if I pressed my foot into the surface of Phobos, okay, what would that look like?
It depends on what you have for material there. It might be very fine material that's missing because if it gets blown into orbit around Mars, it will actually be removed from the system. So maybe the finest material is missing, but it should look just like a blueprint on a plane. Just stuff like that. That would be my prediction.
Although some might say all the slow sticks to your boots.
Yeah, that would happen too, yeah.
Electronics that we've heard about too.
But you would weigh almost nothing on Phobos.
I know, but I would be holding on to something.
So I just want to make a couple of quick comments regarding the possibility of Martian ejecta in the Phobos regolith. Brett Gladman did some back of the envelope look into this. Apparently, the average impact velocity of Martian ejecta onto Phobos is anywhere from 1 to 2 kilometers per second. So that would result generally in major fragmentation of the ejecta. So we would not be expecting to find big boulders. We'd be expecting to find things that are probably pretty well mixed into the finer fraction of the regolith. Second, according to Brett as well, Brett Gladman, we're going to have 30 times more asteroidal contamination of the Phobos regolith than Martian contamination of the Phobos regolith. So for any piece of Mars that you'll be happy to find in the Phobos regolith, you'll have 30 pieces of the asteroid belt to rejoice about as well. And I didn't see the numbers or the calculation. That's just from a conversation I had with Brett, but I remember the numbers specifically. Okay, so Jim is saying this is consistent. Great. All right. The second comment is, and Andy Rifkin, who did the work, should have brought this up. Probably didn't have time, among other things. But whereas Deimos is entirely D-type spectrally, as far as we can tell, Phobos really could be D-type just in appearance. And there's a constant influx of material from Deimos onto Phobos, arriving mostly from the backside, that could be essentially creating a veneer on Phobos that's a contamination from Deimos. So superficially, the two are D-type. To first order, Phobos is D-type, but when you start looking into the details, and so I would like to refer you to a talk we're expecting from Mihaly Horanyi tomorrow, who will in particular describe how
how dust moves around in the Martian system and how things get transferred from Deimos to Phobos. So Mihaly and I think independently Doug Hamilton have been looking into that. So you end up with things that are of order 1 meter of accumulated Deimos dust on the backside of Phobos per million year. Okay, so it's considerable.
This is quite interesting because I would like to go back to the surface of Phobos and finally where could we have the best pristine sample? For example, is it on the blue unit? Following your argument, is it within the crater or around the crater? What is the best place to get a sample which could be the most representative of the interior composition of the body, the very composition?
Yeah, I was just going to say, normally I'm more than happy to take credit for good ideas, but Pascal, I've talked about this in the past, but I think certainly Scott Murchie is more responsible for recently talking about Phobos being covered with Deimos material, and I think it goes quite a bit earlier. I don't know if Dan or Carly were originally responsible for this idea, but the idea of exchanging material is much older.
No, I'm not going to claim responsibility, but this is an important issue, and it gets back to the plea I was making earlier, namely that we really do have to worry about this fine material, and that's, I think, what Pascal raised. And we also know that Phobos and Deimos clearly are related to each other in all their observable properties. Phobos is heterogeneous. Look at that. You know, it's not one homogeneous body, at least in terms of what we see on its surface. So these are things we have to deal with. And certainly it's going to have a lot to do with what's happening with the fine particles that we do see, what its history has been, certainly where it came from. Did it come from a big impact that's been processed, which is probably likely, but what's the last billion years of history? And how has it been redistributed on the surface, which it clearly has been. You can look at the high-resolution, high-res data. There is redistribution going on. So this is an important question, and getting back to where to go to sample, better be careful, because there's a lot of issues that are interwoven here, and I'm sure we'll be discussing them over the next day and a half.
So we would certainly core under the surface to get the more representative sample, but how much deep?
So something else
Yep.
I was thinking we might want to consider, on another angle from the contamination from Mars ejecta is contamination from Phobos ejecta on Phobos, where, say, the Stickney impactor, the ejecta from that could, when it redeposits on other parts of Phobos, when we're investigating that, it depends on really how homogeneous Phobos is. If it's composed of many different parts, then we might not get a representative idea of what a certain part of Phobos is composed of if we were to investigate that. So. Yeah, just another thing to consider in exploration.
I wanted to find out if Phobos has a magnetic field, but I think we had this discussion sometime back where there was an explanation given that there is a dynamo, and so it appears that there does have a magnetic field. The question is, what is its origin? What's the origin of the magnetic field that we have on Phobos?
So I just can say some words because magnetism, this is not my topic, really not. But if we imagine, for example, the giant impact scenario, we can expect, in fact, to remove the magnetic recording of the rocks, and then when they condense, they can record the magnetic field where they are condensed. But I don't think that the magnetic field around Mars at distance as long as 6 Max radii would be enough to be recorded in the condensed material. So just following this idea, we could expect not to have a remnant magnetization at the surface of Phobos. But this is just an idea or an hypothesis. And certainly this is something to measure because we have now instrumentation. We can be accommodated on a lander, and this can measure the magnetic field, the Riemann magnetization of rocks. So I think this is something to investigate.
I just want to add to your comment about the magnetic field. So the Allen Hill meteorite Riemann magnetization shows that the magnetic moment of ancient Mars was comparable to the Earth magnetic field. So the residual magnetization can be expected, given that the Phobos is pretty close to 2.7 the Martian radii only. So it's about the field that I calculate. It's about like 2,000 nanotesla. And actually, if you have a couple of magnetometers placed at different distances, you can even calculate whether the field is dipole or not.
I just want to, if Phobos formed at, let's say, 6 Mars radii and then evolved inward, at 6 Earth radii, would you also get a remnant magnetic field there?
Well, yes, because the dipole field is inverse proportional to the cube of the distance, so that we're talking about only by a factor of 2. It's like 8 times or 10 times weaker. So we're talking about 200 nanotesla, which is still a pretty strong field, which can be measured.
So I just had a quick question based on this idea that Deimos is bearing Phobos and debris. I mean, just for that picture right there, you can see color differences on Phobos. And my question, too, is that you would probably have fairly recent impacts on Phobos that would dig deep enough to maybe get to intrinsic Phobos material and dig through a veneer. So I guess maybe we can talk about this more as the conference goes on, but have people looked at sort of the freshest craters on Phobos, and do they look different from the rest of Phobos? And what about the color differences there? Is that something you would expect?
Go on, Carly.
Yes, people have looked and know it's not simple. And some of the best data is from the high-rise color data, which is the highest color data we have. But you see, just talking about red and blue stuff, you see small, fresh craters that are red in red terrain. In blue terrain, you can see red crater. There's just no regular pattern. Sasha Vasilevsky wrote a nice summary paper about this heterogeneity issues and made a good case that given the evidence that we have now, the bulk character of Phobos probably is much more heterogeneous, blocks of heterogeneity, to meet the observations that he was analyzing.
But Carly, I understand that you would like to have an ideal place to sample. But can you change your mind after doing some reconnaissance when you get closer? Because at OSIRIS-REx, we're spending a year and a half mapping before we choose the sample site.
Absolutely, and I would say that's a really essential criteria for deciding a sampling site.
So I had a quick question. So I was really fascinated by the simulations of the Borealis Basin and the ejecta and the rings, et cetera, in orbit and the origin of Phobos and Deimos. But they were going by so fast, I was so fascinated with them, I forgot to look at the exact data. So this is a naive question in a sense. If you produce Phobos and Deimos from a Borealis ejecta evolution, what happens when things like Hellas form? Okay, could they survive a similar kind of, but maybe smaller evolution of ejecta and or not? Are you with me on that?
What do you mean?
Maybe it's a question for Bill. I don't know. So I'm asking if you produce Phobos and Deimos by ejecta rings accreting and being modified, could they survive something like Hellas?
I think the question is: imagine you had like a Hellas impact or a Utopia impact on Mars. Would you also get a disk that does something interesting? That's what they're.
If you do,
yeah.
do earlier form satellites like Phobos and Deimos survive?
I'm not an expert, so I'm going to defer to people that do SPH code and stuff like Eric. But I would guess there's just not enough energy and mass there to put much into orbit. But you guys agree? Or?
We used to think Hellas was a hell of a big basin, but not so much
anymore. Not anymore.
I think the whole point of having a pretty large impactor is to have that extended disk, and I would think that I'm not super familiar with the Hellas basin and etc. But I would guess that the impact you would get would be even less energetic than Borealis and etc. And that maybe you can put material into orbit, but probably at lower distances, so like a more compact disk with everything inside the synchronous orbit, and you would probably lose all the material to tidal decay. But that may, if you form transient moons, that's always the problem what the transient moon would do to the rest of the system. So I think it's a matter worth looking into. Yeah.
Yeah. Do you have a comment, Eric?
Well, I was sort of, getting back to the original question of the sample return. I want to throw this out there. Like, I can imagine giant impact scenarios. You make the moons, maybe you pollute them with second events or alter them. I mean, they're from a formation of satellites by giant impact. You'll have a mixture of asteroidal material, the impactor, and target material Mars. And then if you have captured asteroids being polluted by other, Mars ejecta, I mean, could we end up with a situation where we bring a sample back, it's got a mix of Mars material, a mix of asteroid-like material, and we can't decide? I mean, that's kind of my nightmare.
The only way I would answer it this way, right? We have lots and lots of samples back from the moon, and we're still fighting, right? So that I think the answer is we'll fight over Mars samples too.
Well, but we're fighting about different things now. We know a lot more, and knowledge answers old questions, but it raises new ones. That's just the game we're in. But do you think we might get samples back or not, be able to decide if it's a giant impact or not? No. You think we'll know? Yes. And why? Absolutely. Why will we know? Oxygen isotopes. They're going to be maybe half from the impactor, half. I mean, oxygen isotopes haven't told us the moon answer. It's sort of obfuscated the question. Oxygen isotopes are pretty much the same on the moon and Earth. Right. I mean, that's contrary. So that's kind of why we're.
Yeah, but.
How about a case of point? Look at the few grains we got from Itikawa. That answered a heck of a lot of questions that are fundamental. And it was just a few grains.
Yeah.
It was wonderful.
So you think they'll be the key to the giant impact or not in the sample?
Let me go for a slightly different question. Do we need samples of both Phobos and Deimos? As noted, Phobos looks different from Deimos. I mean, if you want to, as long as we're coming up with papers that we're going to have 100 co-authors on, next week, maybe they are two different generations of moons. You form Deimos at the first one, everything evolves in, you have another impact from Utopia or whatever, that makes Phobos. That's why they look different. Would you not expect Phobos and Deimos to be the same if you made them from the same disk?
Phobos. I would think that sample return would ask questions that I particularly am interested in. It may not answer your questions, but the thing is that whether Phobos or Deimos are made of Mars material largely or asteroid material, however it got there is fairly immaterial to me. I'm interested in what the stuff is.
You don't care how they form?
I care about what they're made of. Because that really feeds forward to future exploration of Mars. How they formed was, the past is a different country. And so 4 billion years ago, we're always going to have some uncertainty. What I care about is what the mineralogy is today and what you can use that for. And that's really the driving question that a sample return will tell you. Because the academic exercise of whether there was a giant impact or not, although very interesting, is not very functional for the reality of doing, say, in situ resource utilization on Phobos. It makes no difference at all for that. That's why I say that, yes, it will answer the critical questions, but the critical question is, what's the thing made of?
Maybe I just wanted to add to my cavalier statement a little before, is that, if it comes back and you get samples that clearly look like they've been heavily cooked in some fashion, that would seem consistent with the models we just heard today, But let's say it comes back and it looks just like a CI chondrite or a CM chondrite or let's say a CI, like that we're used to. Would that rule out the giant impact model? I don't know. So that's an interesting question. So it's going to teach us something, but it's hard to predict exactly what it'll teach us or whether modelers can get more clever, which we try to be clever. So.
Although I do think you're collecting them from Deimos and Phobos, because I think in the giant impact scenario, most of the models, Deimos and Phobos are same composition.
Yeah, so I was going to make a comment about this because, remember, they're very small. So it's likely that they're an assembly of, maybe a few even smaller bodies. And there's a factor of 10 difference in mass between those two. So I would say that I wouldn't think it completely crazy that, Phobos is a little bit bigger. So maybe it's a little more of a mixture of stuff from the disk, maybe a little bit from the impactor, maybe a little bit from Mars itself. And Deimos is so much smaller that maybe it's much less of a mixture. And maybe it's even maybe a pristine fragment of the giant impact itself that could be representing something a little different. And to comment back on Andy's comment of forming them from two separate impacts, I find it difficult to imagine that you could form Deimos with the first impact and then with the second impact form a second satellite that's going to do stuff so close to Deimos' orbit without jeopardizing Deimos' survival. So I would be more of an advocate of them coming from the same impactor, but maybe because of the mass difference, not representing the same type of mixture of stuff from the disk.
So this is a really great discussion. Jim Green is giving a talk starting at 1 o'clock. And so we're going to go ahead and call it and break for lunch so that we can be back here on time for Jim Green. Okay?
Okay, thank you to our presenter.